Hey everyone, welcome to our introduction to chapter 3, acids and bases. As we dive into this chapter, let's just remember where we've been. We have had a home in Lewis structures. Hopefully we've had enough practice with Lewis structures that we're ready to cut the ties that bind us to that and move on to condensed and even skeletal structures. This idea of skeletal structures or bond line structures, kukui structures, these guys right here are the epitome of organic chemistry. We are going to be using them thoroughly throughout chapter 3. So let's make sure at this point we've practiced enough, we feel relatively comfortable moving on. Again, if things are going too fast with drawing, take a step back and just practice your drawings and practice what information can be obtained from those. Now, we're going to be using the Bronsted-Lowry acid-base definition. I know we've used the Arrhenius definition before in general chemistry. We're not doing a lot of equilibrium reactions here with water, and so the Arrhenius definition is not as appropriate for us. We're going to use the Bronsted-Lowry definition. Bronsted-Lowry was another chemist who was brilliant, and he defined acids and bases as this. Acids donate a proton. Now, we've talked about this before. What does it mean to be a proton? Well, we know hydrogen has one electron in it, and what's in a hydrogen nucleus is one proton, and it has that one electron. This is the idea of hydrogen. Now, a hydrogen plus one cation has one proton and no electrons and no neutrons. So when we're looking at the definition of a proton, we are identifying a proton as this hydrogen plus one cation. That is what acids are defined as by Bronsted-Lowry. Bases, on the other hand, accept a proton. They will be going to pick up that hydrogen plus one cation. So it's this H plus one that will be transferring in from an acid to a base. Now, we recall this general chemistry example with HCl, hydrochloric acid, reacts with water. This was the acid. This was the base. Water was amphoteric. It could be an acid or a base. And in this case, it's a base because what we see is that base and acid exchange the proton. Specifically, the H, the highlighted red H there in HCl, goes to become H3O plus, which we are going to call the conjugate acid. And Cl minus, what's left over, is our conjugate base. Hopefully we remember this general idea from general chemistry of labeling acid base, conjugate acid, and conjugate base. If you need a little definition of the conjugates, again, here they are. A conjugate acid is what results when the base pulls off the proton or accepts the proton. And a conjugate base results in when an acid gives up a proton, right? So looking at that link, the conjugate acid is linked to the base, and the conjugate base is linked to the original acid. So let's look at this example again. Let's just see what's happening. Slightly different molecules now. We still have water, but I wanted to throw in organic chemistry molecules now with it. And so when we look at this oxygen on the left-hand side with a -1 charge, what I want us to be able to see is where is he in the product? Right there. And so what happened? Let's describe the journey that happened for that oxygen. Well, that oxygen must have gained a proton. He had a negative charge and no hydrogen, and now we see in the product that he accepted a proton. So oxygen minus on the reactant side is the base. What it becomes on the right-hand side, on the product side, is the conjugate acid. Water, on the other hand, had the hydrogen. And what we see is that that oxygen, let's just switch colors real quick, that oxygen now lost it in the products. And so we can see water, it must have been the acid. He donated that proton to the base. And what the leftovers become is the conjugate base. We'll start doing some curved arrows and see the actual transfer, but right now what I want us to be able to look at with this example is just the idea that we can verbally in English say what happened, locate and highlight some things. Protons are great to highlight. Those are typically highlighted in your textbook. I also like to highlight other things. I like to start to break down this reaction so that we can truly see what is happening. And kind of walk our way through it to start off with. Now, the making and breaking bonds involves electron movement. So when we use curved arrows, we are actually describing the flow of electrons, just like in resonance. Remember that we'll use the arrow that starts at the 2 electrons at the tail, and they point. The head points to where those electrons are going, right? And so when we're looking at these arrows, we're really just noting the flow. We use the same type of idea of curved arrows that we did with resonance structures, but here the big difference is now that we can actually describe the movement of electrons between different molecules, not just delocalizing electrons and only breaking pi bonds and lone pairs moving. Now we can see lone pairs moving, pi bonds breaking, sigma bonds breaking, atoms coming together, tearing apart. It's going to be fantastic. So let's go ahead and get some movement. We have a base and we have an acid. We're just going to use the generic B and HA right here. We have a conjugate acid. That's what results after the base picks up the proton. And we have the conjugate base, which is resulting after the acid lost the proton. Now, in terms of the curved arrow movements, the base has electrons, and I'm going to take that base's electrons starting at the tail of my arrow and point them, the head, towards the proton itself. When I do that, be very careful. This is not good. What's wrong with that? Negative formal charges do not tell me anything about electrons. The electrons have to move. What's wrong with this? It missed its mark. It's not even pointing at the hydrogen. Don't be lazy. Make sure you're direct with your arrows. The more direct you are with your arrows, think about these as your formation of sentences in organic chemistry. The more direct you are, the clearer you can visualize what's happening, and I can visualize what you know is happening, and you'll get full points. I'm very picky on my arrows only because they are truly telling the story of how the acid and base are reacting. Now, hydrogen here is making a bond with the base. Now, hydrogen cannot have 2 bonds. So as to not break our duet rule, the electrons held between H and A, that covalent bond must break and form a lone pair on A. Let's get some colors on here. These electrons from B minus have now become the covalent bond between B and H. The covalent bond between H and A is now the lone pair on A. So hopefully we can see that flow and see how the sigma bond is forming between the proton and the base, and see how the covalent bond between the H and the A is breaking. All right, let's do it again, just for practice. Now the base is truly attacking the acid. The base is going to pick up a proton. It's a base on a mission, and it wants that proton. So let's go ahead and give it to them. Any lone pair from the oxygen, but make sure you're originating at a lone pair. and make sure it's going to pick up the actual acid portion of the molecule, the proton. Protons can't have two bonds, so oxygen gains that lone pair. Let's just highlight some things again. Taking these lone pairs, it's now going to make one of the bonds between H and O in water. And this bond right here between H and O in the acid is now any old lone pair. It doesn't matter which one, you can just pick one. So that we can truly see that the acid cannot lose its proton without the base taking it. Those two arrows happen together. They happen all in one step. They're exchanging the proton, passing the baton, if you will. Now, the mechanism shows those two arrows that the two pairs of electrons from the base are going to make a new covalent bond, and the two electrons in the covalent bond of the acid are breaking to become a lone pair. Looking at this one, hopefully we can start to see that this is not just an acid-base reaction. This is a multi-step reaction that we will do later on in the semester in chapter 7. But what I really want to focus on real quick is looking at which one of these are called proton transfers, acid-base reactions. So take a minute and kind of just maybe pause the video and see which one actually looks like an acid-base reaction. A proton is transferring from one molecule to the other, from the acid to the base. Hopefully we can see it's this first one, not the second one, and this last one. These first and last steps are the proton transfers. They are both looking like an arrow pointing towards a proton, a hydrogen, and dumping some electrons on the leftovers. Before long, you'll be able to draw mechanisms all the way through, just like this one, not just the acid and base ones. Right now, don't worry about the rest of the curved arrows in the middle. We just want to make sure that we can truly understand a proton transfer. An acid-base reaction, by definition, is going to be the one that has a proton being attacked by a pair of electrons. And so that acid-base idea is going to hold true for all of our Bronsted-Lowry acids and bases. All right, let's get into quantifying acids. Quantifying meaning numbers will be able to be seen here. Now, how do we talk about quantifying acidity? What makes a good acid? Just a couple of things that I want to get out first. Using numerical data to compare how strong acids are. That term strong for an acid literally means that it is reactive. It's going to be good at donating a proton. So what does that actually mean at the grand scheme of things? It means that the bond between H and A, right? If we talked about this guy, this acid bond right here is actually reactive. It's going to be easy to break. The proton wants to leave, right? Those are all kind of different ways we can actually talk about the strong acid idea. Now, a strong base is going to be the same thing, reactive as a base, meaning that it is good at accepting a proton, right? Being able to donate that lone pair, we'll see that type of terminology used a little bit later. Being good at attacking an acid, ready to donate its electrons to make a new covalent bond between itself and the proton. All of those will encompass our idea of strong base. When we talk about weak things, they are the opposites, unreactive. bad at donating, bad at accepting. And so being able to say strong versus weak and really relating it to reactivity here is what we want to focus our attention on. Okay, so Kas, we've done Kas before. A Ka is the acid dissociation constant of the acid when it's dissolved specifically in water. It's a measurement of the acid strength with water as the base. Now, water is used just because it's a universal type solvent and it's everywhere, and we can easily look at the Ka, which was the products, A minus and H3O plus, over the reactant acid. Water in this equilibrium is such a high concentration that it doesn't change. It's also pure liquid, so it's not in the Ka. Now, a Ka is going to be the defining measurement of how strong an acid is. The acid was deemed strong if the Ka was greater than 1. That meant it was strong. If the Ka was less than 1, it's going to be a weak acid. Let's define that real quick. Strong what? A for acid, right? Versus weak acid. We did this a lot with doing ice tables. If you remember doing your ice tables and figuring out the initial, the change, and the equilibrium concentrations, guess what? We don't really do a lot of math in this class. So that's a good thing, I think. We're going to focus on what does it mean to be a strong acid, and how can we use that information to decide whether a reaction will happen or not. That's how we're going to quantify things. So here's the problem with Kas, and we said this a little bit in general chemistry, not too much, but Ka values range from 10 to the minus 50 to 10 to the 10. That is very difficult to work with. The reason behind the Ka being difficult to work with and why organic chemists don't usually use it is we like to do things without calculators. We don't really like to do a lot of math. And so this range is too big for us. That's really crazy to be able to try and handle when we don't even want to start doing long division or let alone pick up a calculator. So what we do instead is we actually take the negative log of the Ka and we get something called a pKa. Just like we took, let's just take a walk down memory lane. A pH is the negative log of the H plus concentration or the H3O plus concentration. That pH idea, P being the negative log function, is how we get this pKa. And this pKa is extremely helpful because what it does is it takes that log base 10 scale and it changes our 10 to the negative 50 to 10 to the 10 range, and it gives us a range of 50 to negative 10 now. So our pKa range has just gotten a little bit easier to handle. What was 10 to the negative 50 as a Ka is now positive 50. And what was 10 to the 10 for the Ka is now negative 10, right? The negative log. So we are taking those exponents, log base 10 scale, right? Taking the exponents, and we're going to negate them, change the sign. So big thing here, the lower the pKa equals, the stronger the acid. Why? It's because when we looked at that 10 to the 10, this is what we said favored products, right? And what I mean by favored products is we looked at that guy and we said 10 to the 10 meant that products over reactants for the Ka had 10 to the 10 more reactants than products. If we look at that number and how we adjust it with the negative log, that number, 10 to the 10, now becomes negative 10. And it still means the same thing. It favors products, right? So the lower the pKa, the stronger the acid. Just like if we remember, the larger the Ka, the stronger the acid. These two things go hand in hand. Just be very, very clear on which one are you talking about, the Ka or the pKa. We'll be dealing with pKas. So when we look at our pKa chart, this chart is the one in the textbook. You do have to know this chart. Why? I know it might seem silly. There's not too many on here. However, but what's really important, this is only a section of the chart that you need to know. I will have the full printout for you of the chart, but you can look at it in the textbook. What's really, really important with these numbers is the idea that you can get a baseline for reactivity.